So usually you ask old people to give this kind of talks, right? You take someone that has 50 years of experience, and you ask them, what did you learn in your career? Okay, so I'm not the best suited person for doing that. I don't know why Flavio asked me. I'm not that old, okay? So how many of you think that I'm older than 30? I mean, you can raise your hand. I will not hurt you, right? Older than 35? Okay, so you guys will not pass the exam tomorrow, okay? So please, Mark, to take their names. It's yeah, that's no. Okay, so to try to give this a little bit more of a light talk, I renamed this talk. I don't know how to use. So I renamed this talk like research horror stories, and let me make two disclaimers. So the first one is that this doesn't mean to be judgmental to anyone. Okay, so these are common mistakes that everyone does, younger people, senior people. I've done many of these mistakes myself several times, and I keep doing that. So it's just important to know what they are, and try to avoid them. But it's not mean to judge anyone. Okay, so that's the first disclaimer. The second disclaimer is that I've never did this talk before, so I might be rambling a little bit and say things that maybe I should not say. So, I mean, like at wedding parties, so usually you have someone that drinks too much and starts saying things that they should not, right? So if that happens, please, cut the microphones. Okay, so let me start with the writing part. Okay, so this talk is divided in three parts: writing, benchmarking, and reproducibility. So some of these things might sound obvious, but it just needed to set up the stage a little bit. So how does research work? Okay, so research 101. So you take a bunch of paper or books and you start reviewing the literature. Okay, you want to do research in networking, you study networking, you see the paper that have been recently published on that, and you try to get an idea of what's happening. And you do this for a while. Okay, study. So that's the first part. Then you try to identify a research problem. Okay, so you see recent papers, you see that maybe something can be improved, and you decide to work on it. You try to come up with a solution. Okay, sometimes this works, sometimes this doesn't. Okay, so in some cases you don't have any clue on how to solve this problem, and you might go back to the previous step. Okay, so this is an iterative process. You go back and forth. So just one thing. Reviewing the literature is a way to get to know what some nice problems might be. Another way is attending events like conferences, keynotes. So for example, the talk by Gil before, I think it was a perfect example of how you can get some open problems also from industry, right? All these things about multiple data centers and so on. So that's also a nice way to get to know which might be some open problems. Okay, then to implement the solution that you thought might solve that problem. Sometimes it works, sometimes it doesn't. So you might need again to go back and design something different. And eventually, hopefully, everything lines up and you write down the paper. Okay, so that's how the process works, or how the process should work. Now, many people, what do they do is that they drop completely the first part. Okay, so we are computer scientists. We are all a bunch of nerds, so we like coding. So sometimes we start coding. We have some nice idea, but we don't actually know which problem are we trying to solve. And that's happened all the time. Okay, younger people, older people, it's quite a common mistake. So you implement something, you try to write down a paper, and then what happens is that the killer reviewer comes and destroys your paper. Okay, so that's quite typical. So what? 2. In our case, it was number 5. I think. So why? So there are 2 things. So this is the first thing that reviewers check. So the motivation, it's clear or not. If it's not clear, the paper 90% is going to be rejected. Okay, so be sure to state the motivation clearly and to know which problem are you trying to solve. The second reason is that there might be a lack of comparison with the state of the art. So if you really don't know what else other people are doing, the reviewer will realize that, and again, we kill your paper. Okay, so let me make another disclaimer. So in this talk, the reviewer is not the monster of the story. Okay, so we are. So in this case, I'm not gonna, I mean, this is funny, but I'm not going to complain about reviewers. I'm going to complain about paper authors. Okay. I will get back on this, okay, on the role of the reviewer in all this process. So that's the first mistake. So be sure to do things like proper. The second mistake is bad writing. Okay, so you did everything perfectly. You spent 9% of your time in designing, implementing, validating, whatever, and then you write the paper the night before the deadline. Okay, Salvatore is smiling because we do this all the time. But I mean, you should not. Okay, so it's bad. Why? Because the reviewer is busy. Okay, so the reviewer it's a professor or a researcher. He must do hundreds of things: teaching, administration, research, and he's gonna review 6, 7 papers for that conference, right? So it doesn't have much time. So, and out of those 6 or 7 papers, maybe 1 or 2 will get accepted. So your paper must really shine, right? Because eventually, if there is something which is not really clear, I mean, you are competing with other papers, right? So you must try to have this paper as clear as you can. And writing this in 1 week usually won't work. Okay, for most people. Some can manage, but it's not easy. So again, this will okay. Now the paper must be informative, of course. There must be all the data that you need there, but it also must be nice. So what nice mean? You have to have nice diagrams, nice plots. I will go back on that. So also the visual part of a paper is important, right? It's not the most important part, but it can help a little bit in increasing your chances of success. And also the reviewer is happy if she or he learns something new. So if you're clearly able to convey what's the new information that you get from this paper compared to what people already know, that's usually a very positive feedback for the reviewer. No? You know, if you read the paper and say, okay, I never thought about this thing in this way, you know, and that's usually the points that you need to stress, like trying to show like what we learn by reading this paper that we didn't already knew before. Okay, in most cases. So there are exceptions to that as well, but usually that's a good. Try to anticipate reviewers' questions. So how do you do that? So usually that's just a matter of experience. After you read many papers, at some point you will realize you will realize some of the questions that reviewers might ask. Okay, and that's a good way also to improve the paper. Okay, so the key point here is that you might have solved a very important problem, have a very smart solution, but then if you are not able to explain it clearly in the paper will not get accepted. And even if it gets accepted, I mean, the purpose eventually is not to have an accepted paper. The purpose is to have an impact on the research community, right? So even if your paper gets accepted, but people that read it don't understand it, that's just one of the things. So just be sure to spend enough time on the writing. Okay, so that's the take-home message. Now, I'll be fast. So of course, if you want to interrupt me at any point, raise your hand. I'm gonna be fast on this part. So how is a paper composed? There is usually an abstract, an introduction, and blah blah blah. So that's a typical. I think that everyone knows that. So I just want to stress a thing here. So there are must the related work be at the beginning or at the end of the paper? So that's it depends. Okay, so it depends on how good you are in letting the reader understand what's the advantage compared to the state of the art in the introduction already. So if the paper is really innovative, usually you just need 2 sentences to explain what's new in your approach. Okay, so you don't need really to dive deeper into related work at this stage. So in those cases, you can just put related work at the end. Why? Because usually, again, reviewers are busy. They might not have enough time to read that paper, so they really want to go into the core of the things as fast as they can. So if you start describing your design at page 4 or 5, the reviewer already got bored. So you need to try to, you know, balance the sections in such a way that you are not too lengthy and you have all the important information where you need them. So usually a good rule is that The first and the last sections should be like um, the nicer ones. So the ones that you write better. Why? Because the first section are the first that the reviewer reads, so the first thing that he or she learns about your paper, and the last section are the last thing that you read before writing the review. So you want him to or her to be happy before starting writing the review. Okay, now in general, how to be a good writer. So there is no way of I mean, it's just something that you learn with experience. And a good way is to read many papers. Okay, so just read a lot. If you have fellow colleagues that work with you, try also to have some discussion, right? Like once per week, just meet for 30 minutes, read the paper beforehand, and just discuss what you think is good or bad about the paper. So learning to judge other people's work, it's a very good way to judge your own work, and then to write better paper. So read a lot. It's not easy, okay? So everyone has this endless reading list. I mean, everyone at all stages of the career. So you keep adding your paper in the reading list, and this reading list keeps getting bigger and bigger. I think I have like 400 papers, and I don't know. I will never manage to read them, of course. But try to find some time each day to read some. Okay, so that's a good way to get to it. So now the next couple of slides, I was not planning to add them. I just added like 10 minutes ago before starting, because like yesterday, some of you asked me something which is kind of related to this, but I mean, I will get to it. And I will go through that with like an happy story. Okay, so academia love story. So there are two researchers that meet at a coffee break at a conference. Okay, so they start chatting each other. They talk. You know, there is a nice vibe. They like each other. Eventually, they go home. Okay, so what do they do when they go home? So the conference was good so far. Okay, so now we might get on the newspaper and okay. So this is not going where you think it's going, right? So one of the two goes back home, open the laptop, and finds you on Facebook or whatever you young guys are using nowadays. Okay, but we are scientists. Okay, so that's not the case. So what will happen is that they will go home and check your Google Scholar. Okay, so that's, I mean, that's something that happens all the time. Okay, so people don't like to admit that, but everyone does that. As soon as you know someone that you didn't know before, you go and check Google Scholar. So that's someone that everyone does. Okay, and I admit that. Okay, but and I think everyone does. So then they see that you have only 4 citations, and they will not write you again. Okay, so broken heart. It's not gonna work. Yeah, exactly. Yeah. That might help a little bit. Yeah. So this is just a joke, and why I'm telling you that, because some people ask me, okay, so this is kind of a controversial thought. Okay, so in research we keep discussing whether it's good to evaluate people with numbers or not. There are good reasons and there are bad reasons for doing that. One bad reason is that we are scientists, so if we know that we are getting evaluated on numbers, we do whatever we can to increase those numbers. And people do good things to increase those numbers and do bad things to increase those numbers. Just don't do unethical things. Okay, so this must be important. It's, I mean, these numbers might determine your career, but don't do unethical things. Also because like this can destroy your career. So there is just a story that I heard 2 weeks ago of there was an open position for a full professorship, and the committee eventually detected that that person did something really nasty to increase those numbers, and they didn't hire him. Okay, and the community is quite small. So if you start going to this kind of event, you will always meet the same people. And we are like old ladies, we chat, you know, and you know what happened to that guy. And that news spreads so fast. So just, and it's, I mean, regardless of that, it's a bad practice. So numbers. So why I'm showing you numbers? Because some people ask me, okay, is it better to write one big paper like, or many small papers? I mean, like, it's better to write a large 20 pages paper to submit at SC, or it's better to write many small papers to submit at workshops? Again, people have different opinions on that. I'm just going to tell you the pro and cons of each. So as a PhD student, you have limited time to get your PhD. In some places, like in Italy, it lasts only for 3 years. And after 3 years, you need to get something out. Okay, otherwise you won't get your PhD. So I can understand people that kind of try to publish something, like even if it's smaller pieces of work. But sometimes this is also called salami publishing, okay? Because you have an idea and you start slicing it and do several papers out of it. I personally prefer the first one. So why? There are a couple of reasons. So the clear reason is that big conferences have a lot of attendees. The community usually looks at those conferences to see what people are doing, right? So if you publish on a big conference, it's more likely that people will see your work compared to a smaller work. Just because the name is, let's say, more famous, and everyone checks every year when the program comes out. Every year I go and check supercomputing, okay, and I read that. If that's a small workshop, your work might not be noticed. So it's just a matter of visibility. Again, these are controversial topics. If you want to discuss, I'm happy to discuss. But there is not. I mean, I can understand the reasons behind both of them. Okay, but it's just important that you know. A strictly related issue is the venue. So where do you submit your paper? Okay, and this is again the same as before. Again, you should not judge papers based on the venues they are published on. There can be very good papers published at unknown workshops, and there can be very bad papers published at super notorious conferences. And I've seen both. But still, again, it's a matter of visibility. So it's up to you. Okay, though there is no right and wrong answer. There is this issue that we have with numbers and metrics. So now the community is like trying to discuss about ways to evaluate people without looking at those numbers, but eventually those numbers will bias people's decision anyway. Okay, so even if officially we are not supposed to look at them, everyone does that. So just be aware of it. And don't cheat. Okay, that's fair. So okay, so that was the part about the writing. Now we'll go into benchmark. So we are HPC people, and at some point we need to test our ideas and see how they perform. Okay. Now this part of the talk is inspired by many other talks and resources I've been used to prepare this part, mostly by a very nice paper by Roberto Belli and Thorsten Ottler. There is also a quite entertaining video on YouTube of Thorsten giving this talk, and also a few other resources. So if you want to know more about these topics, just read those papers. I'll just pick some mistakes from each of those, but you can find more detailed explanations and some more. Okay. Okay, so the first horror story is the one about the mud cherry picking. So what cherry picking means? Okay, so cherry picking it's something which. So it's important to know that. So the reviewer, it's not necessarily a bad person, right? But if it finds something weird, he or she doesn't know if that's weird because you're trying to hide something, or if because you just forget to explain something. And this is, yeah. Or if you're lying as well and you're not showing some results. So this is a very common thing that usually happens. So, and I will make an example with a compiler. Okay, so I propose a new compiler transformation X. I take a famous benchmark like NAS, but I only evaluate this benchmark on a subset of the application. Okay, so the first thing that, as a reviewer, I would ask is why you only consider some of those applications, right? So why? I mean, how did you select them? Did you select those on which you were performing really well, or did you randomly select it? Is there any reason why you didn't consider the other applications? So in some cases, there might be reason why you only select a subset of them, but be sure that you clearly state it. Okay, otherwise that's a good enough reason to kick your paper out on most venues. Because as a reviewer, the first thing I will ask is that, okay, I want to see the data, the missing data, just seeing part of it. So how to fix that? Just use the entire benchmark or the entire data set, and if you don't, just be sure that you have good reasons for that and write them down clearly. Okay. Okay, so yeah, exactly. So that's a very good point. I will go back to that, but again, reviewers are busy and they have to write to evaluate the paper, like, and maybe other 20 papers, which means that when reading the paper they might miss some detail. So that happens all the time. So if you can clearly state it and maybe repeat like in the introduction or like in the most important parts, that's usually a good way to avoid like being killed. So the second one is about metrics. Okay, so performance metrics. And the example here is that we have a paper, it proposes a new algorithm to solve a problem, and they say, okay, the problem using 8 cores is 8 times fast. Okay, and that's the result they show. Is this enough? No. Okay, so this number doesn't tell me anything. I mean, it tells me that the code scales well, but I can have very inefficient sequential code that I can perfectly parallelize and have it scale real. So that number itself, it's not indicative of nothing. Okay. So some people also confuse like speed up and scalability. So speed up is about how much your parallel code is faster compared to the parallel version running on a single core. Scalability, sorry, it's the other way around. Scalability, it's, you see, I get confused as well. So scalability is how fast your code running on 8 core, how faster it is compared to the parallel code running on a single core. Speed up is about how fast it is compared to the best sequential version. So the sequential version time and the parallel version running on one core will have different runtime. So be sure that you specify whether you are computing this number compared to the sequential version or to the parallel version with one single core. And also give absolute numbers. Okay, so I want to see the actual runtime. Why? Because I mean, I might want to compare the runtime on 2 different architectures. I might want to compare with other algorithms that I know that exist and maybe that you didn't consider. So in general, again, the more information you give, the better it is. So be sure to specify everything. Okay, I will show you how you can do this also in a compact way directly in the plots, okay, without taking too much space in the text. Questions so far? Okay. Now, the other issue, I mean, we discussed this already a few times in the last couple of days, is the issues of stragglers. Okay, so Gil mentioned this also this morning. You might have an application running on 1,000 GPUs. One of those GPUs is lower, and it basically slows down the entire application, right? Because everyone eventually needs to wait for the load in some application. Now, why that's an issue? Okay, so let's say that I have a new algorithm, I run it on n GPUs, and then I say the runtime measured by GPU 0 is X. Okay, why GPU 0? Why not GPU 1 or GPU 1000? Okay, so each GPU measures its own time, okay, and I need to report one single number. What number do I report? No, because with the mean, I mean, if the runtime is determined by the slowest process, with the mean you are like you are like underestimating the runtime. It depends on the application, but so there are two things that you can do. One is to let me take 1 second. So why this can happen? This can happen because load unbalance. Okay, so just some node has to compute on more data than some other node. In some application, this might happen. The other reason is performance variability. Okay, so you can have what is called noise. You can have operating system interfering with your application. You can have network congestion, slowing down some nodes more than other ones. So you can have this kind of power. I mean, sometimes even if you buy 2 GPUs of the same model, they will have different characteristics for manufacturing reasons. So one might be a little bit slower than the other. So there are several reasons for that. So ideally, if you can just report the runtime for all the nodes, or like the distribution of the runtime, that's usually not possible for space reasons. So what a normal thing to do is just to report the max. Okay, so if I measure the runtime on each chunk, and they take the longest one. Okay, because eventually for example, for training, we cannot move to the next epoch if that epoch it's over, if it's not over. So I need to wait for the slowest. Okay, so this again depends on the application, but usually if you report like minimum, maximum, average, and a few other metrics, I mean, I would be happy as a reader. Okay, the more you tell me, the rule is the more you tell me, the less opportunities I have to kill you. Okay, and I don't want to kill peppers, right? And usually reviewers try to find good things in peppers, but if you don't give them the information they look for, it's gonna be a problem. Okay, so a kind of related problem is performance variability. We mentioned it, and this is also super common. Okay, so this is super, and it's really bad. So you evaluate a new algorithm, you do one run, and you report that number. Okay, so okay, I ran my algorithm on 1,000 nodes. It took 20 seconds. That's a number. That's bad. Okay, why? Because runtimes, especially on supercomputers, are not determined. So try to run something on a large scale system, and you will observe several. I mean, a lot of variability in your runtime. Okay, so it takes 20 seconds now, but maybe you run in 2 minutes, and it will take 40 seconds. Okay, so, and this happens, right? It's not. I'm not making up this number. Okay, so I've seen this happen. Exactly the same condition, exactly the same input, exactly the same application. You run it twice, you get 2x performance. So how to fix that? So again, this variability can happen for different reasons. There is interference by the operating system, network noise, and also this variability increases with the number of nodes. So the more nodes you use, the more fluctuation you will see. What's the solution to that? Run it multiple times and report some measure of variability. So usually confidence interval, 95% confidence interval, it's a good variability measure. The best thing to do would actually be to report the entire data distribution. Okay, so you do a nice KDE plot or violin plot or whatever, and you report all the samples that you measure. Okay, you see a curve or something, and that will give. I mean, there is no more information than that you can give to the reviewer. He knows everything. Okay, you run 1,000 times, and he will see how those run times are distributed. So if you want to know more about these variability issues, I put there some red. Okay, so I'm not going to discuss them, but this is quite a big problem. Now, how to report this data distribution, right? Yeah. Okay, so that's a very good question. So you will find the answer in that paper. So, but let me answer you this question. So you should run it long enough. So you should run it like I don't know, 5 times. Measure the confidence interval. If the confidence interval is small enough, like 5% around the median, you stop. Otherwise, you run and you keep doing that until the confidence interval gets small enough. Which means that if it's small enough, you are quite confident that that's the actual mean of the series. Yeah, it depends on many things. But usually you measure for a while, and if the confidence interval is small enough, you stop. Otherwise, you keep running. And be sure to document all of that, of course, in the paper. So how to show variability? This is the lazy solution. A lot of people do that. Okay, this is just usually a parameter in your scripting plot, and you say, okay, I show some measure of performance variability. Don't do that. Okay, so it's bad. Why it's bad? I will show you this with an example. So it doesn't tell me much. Okay, this is like I think standard deviation, but I have no idea on how the distribution of the data looks like. Okay, so let's see this example. A slightly better way is to use what is called box plots. Okay, so you might have seen those. So this bar here is usually the median. So these two lines here are the first and the third quartile. These bars here are usually like 1.5 times the interquartile range. I mean, it depends on the plotting. Okay, but anything that falls over those lines are outliers. Okay, so these points here are like unlucky runs. Okay, this is not a typical case. It's something like strange that happens. So this is already a much better way of showing this distribution compared to that. An even better way would be actually to show the real distribution. So here we have each point is a run, and you have the runtime for that run. Okay, so you have a bunch of points, and I look at those points and I understand what's going on there. Now, the important thing here is that here these two distributions look quite similar, right? If I see the quartiles, they look similar, but when I see the actual distribution, they are totally different. So here we have a distribution that never goes below 0, right? And if I just show that, this is an information that ends. So this is the ideal case. It's not always possible to do that for several reasons, but if you can, just showing the distribution is the best thing you can, because like these box plots and especially the bar plots are quite misleading. Questions? Yeah. Yeah, you can also do that. So like in Seaborn, you can overlap multiple. It might be harder to read, but you can overlap violin plots, and I will show this later. Violin plots and box plots. That's going to be easier to read. Yeah. Okay. Yeah, I will go. I will go to that. I will. Okay. So it's tricky. So how to report this data distribution more in general? So if you have enough space in your paper, the nice thing to do is to actually to report something like a KD plot, and to start marking on the plot all the relevant information. So here I have the distribution. Okay, so this is the density function. This is the runtime. But I can start annotating things, right? I can start annotating the 95% percentile. I can annotate the maximum runtime I measured. I can annotate the minimum, the median, the mean, whatever. Okay, again, the more information you give, the better it is. Okay, so percentile, especially like 95 and 99 percentile, are quite important in some domains. So if you give this information, the reviewer will be happy. You can do this in a compact way. So I discussed this before. This is a box plot. So usually you can have this kind of notch, which shows the confidence interval. So the smaller the notch is, the more confident you are that that's the actual median. Or you can do violin plot. Okay, so violin plots are one of my favorite type of plots because they are super compact and they show all the things. So how do we read that? So let's split this into half. Let's consider this half. Let's rotate it by 90 degrees, and that's exactly that. Okay, so a violin plot is just a density plot rotated by 90 degrees. Okay, so this is my distribution. Just imagine this rotated like that. And again, I can put all the information I need there. I can annotate the median, the mean, the maximum, whatever. If you want even to be more fancy and precise, you can combine them both. Okay, so you will have all the information that you need there. And as you can see, this doesn't take more space than a bar plot. Okay, so this eventually takes the exact same space of a bar plot, but gives me much, much more information. Questions? Okay, so this is good, okay, but just be sure that you have enough samples. Okay, when you have a few samples, like weird things can happen. If you just have a few samples, let's say that we have these three violin plots. So the first problem is that they look bad. Okay, so they don't even look like violin, but they also look quite similar. Okay, so I might think that okay, the distribution, those distributions are the same. If I plot them as box plot, I will start seeing some differences. If I plot the actual samples, they are basically the same. Okay, it's just 5 samples. So if you have few samples, don't use box plots. It just doesn't make sense. So again, you should be critical, like in deciding when to use what. Okay, so not all the tools are always the best. I mean, there are things to use depending on the situation. So yeah. Exactly. It looks like you run a lot of experiments, but you just run 5. So and here in this GitHub repository, which is called friends, don't let friends making bad plots. Okay? You will find much more of those examples. Okay, so I will now go more on the plotting side. I will keep talking about plot. Okay? It's a topic I particularly like. Now, that's a quite common mistake that many people do. So what's the issue with this plot? Maybe you don't see it. The axis doesn't start at 0. Okay, so that's quite a common trick to hide like things that, I mean, to make differences look larger. Okay, and it's also, I mean, I have to be honest, it's also hard for me to detect it. So sometimes I read papers and I don't realize that they are doing that. Again, because I mean, you are reading a bunch of papers. But if I see that, okay, that's not gonna be good. Okay, because it's really it's cheating. Okay, so it seems here that the difference between this one and this one is 5 times, but actually it's probably 10% or something. So just show the entire axis. Okay, so in some specific cases, especially when you use violin plots, it might have sense to have the y-axis not starting from 0. Why? Because sometimes what happens is that if the axis starts from 0 and the median is like at a very high point, those violins will collapse. So you will just see lines. You will not see anything. So in those cases, it might be helpful to have an axis which doesn't start from 0, but be sure that this is explicit. Okay, so you don't want to scare the reviewer. So be sure, okay, the axis in this plot, please note that the axis does not start from 0. Okay, so I know, and I don't get scared, and I will try to understand better. Okay, so let me go a little bit more on the plots. So the next story is about scary plotter and the dark arts of data visualization. So I'll just give you a few suggestions on how to make nice and informative plots. And many of these things I learned from other people like Salvo and other of my former colleagues. So it's just something that you learn by seeing what other people are doing. So just try to. This is also a good reason for reading many papers. Okay, when you read good papers, you will find some tricks, and then you can try to apply it. So what's the story here? You made a very nice paper. It's very nicely written, but then you have terrible plot. Okay, are either unclear or not very informative or whatever. So, and the first thing to do is to choose the right tool for plotting the data. Okay, so don't use spreadsheet to plot data. Okay, so I won't make names, but don't use that tool that starts with E and ends with cell. Okay, don't do that because that's bad. So usually that's a big red alarm sound because the plot just looks and the paper doesn't look, let's say, professional. Okay, so that's again, it's not a reason for rejecting your paper, but it might add some bias in the reviewer head. It might start thinking, okay, these guys, I mean, are a little bit sloppy. I'm not sure if I have really to trust them. So it's not a reason per se, but it might add some bias in the review. So what are some suggestions? I personally like Seaborn. It's a Python tool. It has support for pandas, data frame, and a lot of other things. It simplifies a lot, many things with data processing and but there are many others. Okay, so there is matplotlib, there is R, which is also quite good. There is bokeh and some more exotic thing like plotly and whatever. So use whatever you want. There is no also GNU-plot if you live in the 80s. Okay, so again, this doesn't mean to be judgmental. Okay, I've been using GNU-plot also for a while. I know that some of my students use it. I don't know why, but we don't live in the 80s anymore, right? So there are simpler tools for doing that. So just use Python, and I mean Python is really good. And again, choose the most appropriate plot type. So at this link you will find like a lot of different ways to plot data, some of which I've never heard before. But it's nice because the right plot to use depends really on what you want to show. Okay, sometimes you want to show heat maps. Sometimes you want to show radar plots. There are a lot of fancy plots that you can use, and usually they are. I mean, just select the best thing because that's also the best way for who reads to understand what the data is. Okay, so just don't stick always to doing bar plot. That's boring and just bad. Okay, so let me give a few tips on how to make your plot nicer. So the first tip is quite easy. So report bounds. Okay, so let's say that you are evaluating a system and you are measuring, I don't know, network band. Okay, so if you just give me that number doesn't tell me anything. Okay, so I need to know what's the upper bound or the lower bound, and it's usually a good practice to report that in the plot. Okay, so I will show some examples from some of my papers, not because they are particularly good ones, but just because I know the reasoning I had. I mean, when I was writing that. Okay, so I can motivate why I did things in some way. This case, okay, we were evaluating a system. We were evaluating the global band. Okay, so we had a system with 1,000 nodes, and we were evaluating all-to-all band. Okay, so what do? You put some horizontal lines and say this is the speed of light or the theoretical peak. Okay, I know that I computed with pen and paper, and the system cannot be faster than that. Okay, how close do I get to that? Okay, so by looking at the plot, I immediately see it. So it's not enough to write this number in the text, okay? Because the viewer can just look at the plot and he needs to know anything from there. Okay. Again, the more information you give, the better it is. So we also put some other information here. We also put a little bit of a diagram. We didn't have space for that paper, so and Talbot decided to put the diagram in the plot. Okay, so it was just the only white space we had for that paper. So again, related to that, exploit white space to improve plot viability. So in this case, we were evaluating one algorithm which is called swing with other algorithms. Okay, what's the issue with that plot? So you have no idea of what's happening here. Okay, you have no clue. So what some people do when you have this kind of plot, this is especially true for network bandwidth. What they do is they plot this in logarithmic scale, but I don't like that. I think it's even worse. So I mean, it's just my opinion. Okay, so what we did in this case is to zoom in. So we have some white space, we zoom in, and we show how is the difference between those algorithms. And then we did something more. We added labels. Okay, so you can see here that the green line is not in the plot because the green line is it performs much worse than the other ones, so it didn't fit here. And we put a label here and say, okay, look, that green line is 7 milliseconds. Okay, it's out of the chart. It's 2 orders of magnitude higher. So and that's one thing. So we still have some more white space. So why don't we add something else? And we added another small plot. In this case, this shows the percentage of gain between the blue line and the best of the other lines. So we are showing how much our algorithm is better compared to the best state-of-the-art algorithm. Okay, so it's the same information that you have here, but here it's quite hard to understand it like immediately. But they look up there and they see, okay, when it's green is good, when it's red is bad. So I can immediately see how that performs. Okay. We also have some small letters here. What's those letters are? It's the name of the second best algorithm. Okay, it's the name of the best state-of-the-art algorithm with which we are comparing. So again, the more information you give, the easier is to get this information. The less time the reviewer will spend trying to understand things on his own, on her own. What else? Again, you can do the same. Like for example, in this case, yeah, yeah. That's a very good point. So thank you for pointing that out. So, and this is especially a problem like for people that have like daltonism or like issues with vision and that they cannot distinguish color, or just old, yeah. So this, of course, is gonna be hard to read in black and white. But we did something there. So we didn't put a legend with colors. We put labels on the lines. So even if you print in black and white, you will still understand which line is which. Okay. If you put the traditional labels on the top with colors, you will not see anymore. So And we also have different markets. Yeah. So again, I mean, this might sound like psycho. I mean, I might sound like a psychopath a little bit, I realize, but all those details eventually is what makes a little bit of a difference. Okay, it's not the reason why your paper will get accepted, but you know, it's gonna improve a little bit your chances of getting accepted, and especially of people understanding those data. Okay, it's easier to understand those data compared to other ways of showing them. Other example. So here there is distribution again. Uh, we write things in the plot itself. Okay, so for example, 70% of events last than 10 minutes. This is something that I will hardly understand by just looking at the plot. Okay, it's not super clear, but if I write them clearly, so if that's the most important message of my paper, I want the reviewer to get it. So I put annotations in the plot so that the plot must speak for itself in some sense. Okay, I should be able ideally to understand the plot without reading the text. That's not always possible, but it's nice to try to have that as a goal. Again, labels everywhere. So in this case, for example, you can also exploit the x-axis to put more information. So here, for example, I added minimum and maximum, which were not shown in the box plot. I explain what a box plot is, because maybe someone never seen a box plot before. So I say, okay, this is the mean, this is the median, this is the percentile, and so on. So, and even if someone has seen a box plot before, the meaning of those whiskers here change according to the plotting tool that you are using. So it's better to stress this out and say, okay, these are not minimum and maximum, these are 5th and 95th percent. Okay. Last part, this is gonna be fast. It's reproducibility. Yes. Yeah. Yeah. That's a yeah. 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 So that's a reasonable point, right? So there is a high risk that you do a little bit too much. Okay, so that's a very good point. So finding, and we know people that so we know people that do even worse than that. But I mean, it's just a balance that you need to find. It's a matter of personal taste, but it's true. I mean, there is a high risk of putting too much stuff in the paper. Not only for the plots, actually. Okay, this can also happen in diagrams, in text, whatever. And I also get scared when I find two papers that are too dense. If there is too much stuff in the paper and not much white space, I start getting palpitation, and yeah, I go and cry in the bottom. So let me get back to that. I will talk about reproducibility. So that was just part of the story. Eventually, what if someone reads your paper and wants to use it, to use your algorithm for computing something? So maybe they invented a similar algorithm and they want to compare it with your algorithm. Uh, so that's not easy. Again, this is a matter of impact, right? So if your algorithm is reproducible, it's more likely that people will use it. If it's not, and you don't provide the code or you don't provide instructions, no one will care about it. So just try to release code and document it properly, and so on and so forth. So you might have seen those badges. So in some papers have those stickers on top of it. What do they represent? Those are badges that tells you whether the code is available, if the code can actually be used, and if someone actually used the code and got the same results that you claim in the paper. Okay, so these results reproduced means that there have been people that downloaded the code and got exactly the same results that you claim you will get by using your algorithm. Again, what they are useful for, I mean, it just gives the impression that the paper, let's say, is more solid, that someone validated also the computational part of the paper, not only the idea. Now, in some conferences, this is mandatory, or at least in some other conferences, it's optional. In some other conferences, there is no way of doing that. What I suggest is that even if the conference does not require doing that, do that. It's usually okay. I will tell you a few rules. Of course, it requires time. Okay, so we are all saturated with things to do, and this is just yet another thing to do. But I think in the long term, this will be good for your work. Okay, so usually what you do is to release the source code. Of course, usually you do this on GitHub. It's even better if you associate a DOI. So it's basically a number that points to a very specific version of the code that is the one that you use for the paper. Because if you put a GitHub URL, you might update the code, and it's not exactly the version that you use for that paper. And there are some websites like Zenodo that helps you in doing that. So document the code properly. Okay, so this is something I'm telling you, but which I don't. But at least write a README. Okay, so at least write a README where you tell people how to use that. And also, it would be nice if you simplify its usage as much as possible. If you provide this with a container, people will be happy. They don't need to install anything. They will just use it. And of course, that's not always possible. If you run large-scale MPI application, then providing a container for that is going to be it. Document the experimental setup. So specify the CPU you use, the GPU you use, the RAM model, the RAM type. Again, the more information you give, the better it is. The software setup, and any data sets or benchmarks that you use. Okay. So again, some conferences don't ask for that. If you want to do this anyway, I put here some URLs of conferences that have this as a mandatory step and gives suggestion on how to do this stuff. And here you will find one of these artifacts. So we won the best artifact award of supercomputing a few years ago. So it might be a nice example of how an artifact is structured and how it's documented. So let me finish on a positive note, okay? And give some suggestions. So now here I will put the head of the old man, okay? So do not take reviews personally, okay? So this is hard. So you send the paper, you spend months working on it, and then someone says you very bad things about your research, and that's hard, especially at the beginning. So try to do not take it personally. I mean, in this job, you will always be judged. I mean, everything you do is public. People will talk about your work. They will judge you. So it's fine, right? It's not they are not judging you as a person. They are judging your work, and they might be right. They might be wrong, but it's life. Just don't try to take it too personal. Also, some people might agree or not. There is a bit of randomness in the review process. Okay, so what do I mean? I don't mean that the reviewer will throw a coin and decide to accept or reject. It just means that we are humans and we can make mistakes. Okay, so sometimes you might be unlucky and find a reviewer that maybe didn't really get your paper, or maybe you were not good enough to explain it. But there is a bit of randomness in the process. That's okay. I mean, very good paper usually get go. Very bad paper gets out. Everything in the middle, it might depend on a few other things. So if you never had a rejected paper, it means that you're not trying hard enough. Okay. So who of you did not ever had a rejected paper? Okay, you're shy. But anyway, sorry. Okay, that's good. That's good. So it's try. I mean, the suggestion I give is try to aim very high. Okay, it's better to try and fail that's not to try. So there was some point in my career, especially at the beginning, where I was thinking that people that got paper at supercomputing were some kind of monster or heroes, like, and I was thinking, okay, I will never do that. It's just out of the way. And then at some point I tried and it worked. So do it, right? There is, try to set a very high goal. If in the worst case you will get reviews, they will criticize your work, but you will learn something, right? Those people usually give very good reviews. So even if they are critical for your work, you will maybe get some ideas on how to improve. So just aim very high. Again, and different people might judge your work different. Okay, and I just show you. I just discussed two examples. So the first one is a paper rejected a few years ago harshly at SC. We submitted the year after that. It was candidated for best paper. So just 1 year after. Okay, so we improved this a little bit, but more or less was the same paper. It happened, right? Another example, a paper was rejected at a conference. It was immediately resubmitted as it was to a better conference, let's say, or more prestigious conference, and it was accepted. Okay, like for full acceptance, something like that. So it happens, right? So this is why I say that there is a little bit of randomness. It just happens. So don't get mad or don't get sad if your paper gets rejected. Sometimes it's just a matter of luck and retrying again. Yeah. So let me conclude. So okay, the take-home message is here that writing should not be rushed. Okay, so that's an important part of your career. So don't do that the last week. So try to plan it well ahead of time and spend some time in doing that, because as you can see here, like tuning all these little details takes some effort. So some people disagree on that. Be a perfectionist. Okay, perfection does not exist, and if you try to be a perfectionist, you will work on your paper forever. Okay, so even paper that I got accepted, I find 100 reasons and 100 ways to improve it. Okay, so at some point, of course, you have to stop. But try to aim very high. So one thing we discussed in the last few days is that this should be true also for presentation. Okay, so that's another horror story which I would love to give, but I think that people should also, like, learn how to do a presentation. That's also an important part, because eventually you go to a conference, you present your paper. If the presentation is bad, people will just forget about it. Late. Yeah, exactly. Yeah, like myself. Yeah. You see, I mean, this wasn't meant to be judgmental. Okay, you will make the same mistakes. Read, review, and discuss with your colleagues or with supervisor. That's usually a nice way. If you have the chance, try to get involved, like in reviewing papers. Like if your supervisor is involved in some program committee, ask him or her if you can review some papers. That's usually a good way to compare how do you judge a paper with how the rest of the community judge it, and you learn a lot from that. Okay, you see different points of view, you discuss it, so it's a very nice way to become more self-critical. Pay attention to benchmarking and data reporting mistakes, and be sure that your work is reproducible. Okay, so all in all, don't be a monster, right?